Hello, everybody. I'd like to welcome you to the talk Cost-Effective Data Annotation with Bayesian Experimental Design by Quan Nguyen. Thank you so much for being a part of the conference, and I'll let you take off from here.
Alrighty, thanks, Stephen. Welcome everyone to my talk. Today we're going to be learning about a technique from statistics and probability, but people have been increasingly using this in machine learning, where we want to derive ways of picking which data points to label in order to best train a model or learn about something of interest. My name is Quan. I'm currently doing research at Princeton University as a postdoc, and my research centers around Bayesian machine learning decision making under uncertainty, which is a broad category that the topic of this talk falls under. So I'm very excited to go through the materials with you. Feel free to connect with me via any of these social media links if you like. All right, so to get started, let's look at three seemingly unconnected examples, which is Wheel of Fortune, learning about physics by developing physical models of the world, and designing political surveys. What do these examples have in common? In each of these examples, you have to perform experiments in order to learn about something of interest. So in Wheel of Fortune, if you're not familiar with the game, you have to basically guess specific letters, and the game will tell you whether a hidden word contains the letter that you've guessed or not. And the game is won by you correctly guessing which hidden word that is. So in this very particular example, there are good guesses and there are bad guesses, right? As you can imagine. In this prompt, we can see that a guess of the letter F would be a very good guess because it will most likely complete this hidden prompt, which is, as you can probably guess, is Wheel of Fortune. So if you guess the letter F, you will gain a lot of positive utility. That is, you will win some points from this game, and you're more likely to win this game. If you guess a bad letter, for example, Z here, which is pretty unlikely to belong to this hidden word, then you will lose some utility or gain negative utility. So this is all to say that in this particular example of Wheel of Fortune, there are good actions to take, good experiments to perform, and bad experiments to perform. And this is the same thing for the other example too. If you're designing a survey where you are interested in learning about the political leanings of the participants of your survey, then there are good questions that you can include in the survey, such as who did the participant vote for in some particular election year, which will allow you to gain a lot of information about the participants. There are also bad questions that you can include, such as was the participant born before 1800, which the answer is most likely yes, right? Because it was, sorry, no. Yes, after 1800. Yeah, because that was a long time ago. And by including bad questions, right, you lose some utility because you are wasting a lot of time from your participants, and you're uh, basically crowding your survey with a basically useless question. So in this particular example too, there are good experiments to perform and bad experiments to perform. So the question becomes, right, in each of these examples, how can you systematically decide which experiments are good to perform, which experiments are bad, so that you can avoid them, and which experiments are the best so that you can gain the most information about what you're interested in. Either it is the hidden word in Wheel of Fortune or the political leanings of your participants while conducting a survey. So across all of these examples, we have a model of what is going on. First, we model the data gathering process as querying an oracle. And this oracle stands for some data generating process, or it could be a human, a participant that you would like to learn about, or some process of interest that is hidden away from you. So you query this oracle for data labels. Every time you query this oracle, you obtain a label of a data point. But what makes this problem challenging is that queries are expensive, right? Every time you query the oracle, you incur some costs, either in terms of time or money or some safety critical condition. In Wheel of Fortune, again, to coming back to the game, every time you make a guess, if you guess wrong, then you lose your turn. So that makes up the cost of querying the oracle there. Every time you ask a participant to fill out a survey, it is also a costly action because most of the time you have to pay people to take your survey, and so you have to pay some monetary cost, right? So the idea here is that because queries are expensive, you want to be as efficiently as possible about what you are querying. So what you want to do is to target the data points whose labels yield the most information about what you're interested in. And so far, I've been pretty vague about how to actually define what we're interested in is, but we'll see some examples later. Here is just the overarching model of what we're trying to achieve. So this is where the topic of this talk comes in, which is called Bayesian experimental design. And it's not a machine learning model. It's not a particular algorithm, right? It's more like a framework of how to make decisions under uncertainty. And how it works is that first we will build a predictive model on what we're interested in. So this model basically quantifies what we know about the world, but this can be a statistical or machine learning model. This could be a model that tells you what possible words it could be in Wheel of Fortune, or how people generally think while conducting a political survey, etc. Now, what you do with this model is that you will use it to guide which experiments you want to perform, which data points you want to label, in order to maximize information about the word or what you're interested in. So you use this model to answer the question, which letter to guess next in Wheel of Fortune, or which questions to include in your survey to find, to obtain the most information as possible. After using the model to pick out the most informative experiment, you will perform that experiment. You will query that data point to obtain its label, and by taking an action on the word, affecting the word, and that will yield some data that you requested, right? In the Wheel of Fortune example, this is whether the letter is in the hidden word or not. While conducting a survey, this would be you obtaining the actual responses from the participants of your survey, and having labeled those data points, you will add those new data points into your model and retrain the model that you had in the beginning. And this whole process repeats until you are satisfied with your knowledge about the word. So as you can see, this is quite an end-to-end process, right? It's not your usual machine learning, intro to machine learning example where you just have a data set and then you train a model and make some predictions and that's it. Here you train a model and then you use the predictions made by that model to find new data points, and those data points are then added to the training data, and the model is retrained again so that it can guide future experiments. Again, the goal here is we want to use this model to find which experiments to perform in order to gain the most information as possible. And that makes up the what we call the Bayesian experimental design loop that we see here. So that is the overarching model of Bayesian experimental design. And here I'd like to basically dive a little bit deeper into how this actually works. And we'll start out with a model, the first step in the loop that we saw, which is typically a probabilistic model built in a Bayesian way. And if you're not familiar with Bayesian language, don't worry. Basically, what we want to do is we have an unknown quantity of interest that we want to learn about. It is either the hidden word in Wheel of Fortune or people's political leanings in the other example. We also have a data set of training data points. Now, what we will do is we will place a distribution that acts as a Bayesian prior on this quantity of that we're interested in, theta. Basically, a prior distribution describes the behavior of theta without any data. Now, what we'll do is we will also build an observation model that describes how data are generated based on the unknown quantity theta. So it describes the relationship. If you were to know theta already, then how would you generate the data that you have observed so far? And by performing some Bayesian statistics, what you can do is you can compute what we call a posterior distribution of theta, which describes the behavior of theta now conditioned on the data that you have seen. You can think of this as training a machine learning model on some data and using that model to predict theta. This is different from the prior because the prior is not conditioned on any data, but with the posterior, you have updated that distribution to factor in the data that you have observed so far. So this is basically a Bayesian updating process. All you need to know about this process is that given the posterior distribution, you have a way to describe what you believe about the behavior of the theta, what you're really interested in, conditioned on the data that you have gathered. Now, I'd like to use this very simple example that you might have seen in your Intro to Bayesian Statistics class, where it illustrates the idea of using a probability distribution to describe what we believe about a random variable of interest. So let's imagine this is a coin flipping example, right? Where you have a coin that is possibly biased. So you flip it a bunch of times, and if it's biased towards heads with some probability, then you'll see heads more often than tails, or vice versa. And what you really want to do is you want to find the bias of this coin. That is, every time you flip it, what is the actual unknown probability that you will get heads, right? If it is an absolutely biased coin, then this probability will be very close to 1 or 0 to indicate the bias of the coin. If it's not a biased coin, then this probability will be very close to 0.5, right? 50-50 either way. So what you do as a Bayesian statistician is that you will model the unknown probability of heads described with the x-axis here as a uniform distribution between 0 and 1. So you don't have any prior knowledge about the bias of a coin, so you say that every number between 0 and 1 is equally likely. Now, what you want to do is you want to flip the coins a bunch of times and observe how, after a bunch of flips, how many heads you actually get, and use that data to update what you believe about the probability of heads. So let's imagine that you flip it twice, and what you get is you get 2 heads. So both times you get heads. By using the Bayesian update rule that we saw in the previous slide, we don't need to go deeply into the math here. We will update the uniform distribution we have on the left to this more skewed distribution where it assigns more mass to the right-hand side because we saw 2 heads after 2 flips, right? 2 trials. So naturally, we want to assign more probability to the fact that this coin is probably biased towards a large probability of heads. So you can imagine repeating multiple experiments in the same way. So for example, here after 10 trials, we observe 8 heads, and the probability distribution is updated accordingly. And as you have more and more trials, what you notice is that this distribution slowly gets narrower and narrower to describe your increasing confidence in your estimate. After 500 trials, you have roughly 230 heads, and the probability distribution centers very closely around slightly less than 0.5, which is saying that not only you are predicting that the bias is slightly less than 0.5, but you are increasingly confident in that estimate as well, which is only natural, right? Because you have more and more data to support your estimate. This slide basically serves as an illustration of how you can use a probability distribution to describe what you believe in an unknown quantity of interest. In this case, is the bias of coin representing the probability of getting ahead. And by using the Bayesian update rule, we can compute what we saw as posterior probability representing our belief condition on the data. Okay, so far we've talked about the model, the Bayesian model, but if you remember, it is only one part of the Bayesian experimental design loop. The other part is using this model to pick out the experiment that gives you the most information. And this basically comes down to maximizing the information you have about the the quantity of interest. So let's think a little bit about what we really want by performing experiments. Well, we can roughly say that we want to know as much as possible about theta, the quantity of interest, but how can we quantify this goal of knowing as much as possible about theta? And one way to quantify this is we can say that we want to decrease our uncertainty in our belief about theta. And remember, our belief is represented by a probability distribution. And if you have seen this quantity before, then this might make a lot of sense to you. But we appeal to this quantity called the Shannon entropy of a probability distribution, defined to be the negative sum of each probability multiplied by the log of that probability. And we'll see an example of why Shannon entropy is a reasonable quantification of uncertainty later. But let's assume that Shannon entropy is a established way to quantify how much uncertainty you have in a probability distribution, and therefore we will use it to make it a quantity that we want to decrease as a goal of maximizing information about theta. Now, what we want to do is we want to gather more data so that when our model is conditioned on this new data that we gather, the Shannon entropy is as low as possible. But the problem is we won't be able to know how much the Shannon entropy will decrease until we actually gather the data. So this pretty much sets up a challenging problem where we want to find the data that minimizes the Shannon entropy, but we don't actually know which data minimizes the Shannon entropy until we actually query the label of that data, right? So what we decide to do is to use the expected value of the Shannon entropy when conditioned on new data. Remember, we don't know the label of the data that we can possibly query, but we have a probabilistic belief about the behavior of that model thanks to a Bayesian model. So what we want to do is we want to find the data point that minimizes the expected value of the Shannon entropy when conditioned on the new data. And this expected value is averaged across all possible labels. I know this math might look quite intimidating, but the idea here is fairly simple. We want to minimize the Shannon entropy, which is a quantification of uncertainty that we have about theta. And what we want to do is want to find the data point that on average decreases that Shannon entropy maximally. So that's what we will do. Now, on this slide, I want to come back to the example we saw earlier about coin flipping and show you that using the Shannon entropy is a good way to quantify uncertainty. So what you can do is to compute the Shannon entropy, whose formula we just saw earlier, right? It's the negative sum of P log P across these distributions. And because we know these distributions already, we can easily compute the Shannon entropies. Here here we can see the corresponding Shannon entropies, where we see a reasonable trend that the Shannon entropy decreases as the distribution becomes narrower and narrower, to quantify the fact that the more confident you are about the quantity that you're estimating using this distribution, the Shannon entropy becomes lower and lower. So this illustrates to us that the Shannon entropy is a reasonable quantification of what of the level of uncertainty you have about the quantity of interest. Okay, so I've talked a lot about the formal process of Bayesian experimental design, and all of this might appear very vague to you. So let's try to familiarize ourselves with the process by actually doing following an example. And this is one of my favorite Bayesian experimental design examples. And the setup of this example is this, right? You are given a sorted array of 100 numbers and a target Z that you know is within this sorted array, but you don't know the actual index of this target. And what you want to do is you want to find the index of this target by comparing Z against different elements within this sorted array. And given this prompt, if this problem sounds suspiciously familiar to you and you think that you have a pretty good solution to this problem, hang on to that thought because we'll come back to that. But let's try to approach this from a fresh angle, right? From the angle of Bayesian experimental design. Remember, what we want to do is we want to place a prior on the index of Z, which is the quantity that we are interested in. Here we will place a uniform prior on Z. So it could be at the first index, second index, or the last index. Each index has an equal probability of 1%. Now what we want to do is we want, again, to compute the expected entropy that we'll get after performing a comparison. So let's imagine when we do a comparison, what would be the entropy in different scenarios that we can encounter while doing that comparison. So imagine if you were to compare Z against the first index, the number of the first index, then there are two possible scenarios. The first is that you realize that x1 is exactly equal to Z, which only happens 1% of the time, right, according to your prior belief. But 99% of the time, x1 is actually less than Z. And in each of these scenarios, what you do is you will compute the Shannon entropy according to your posterior belief. So if x1 is indeed equal to Z, then you'll have 100% probability assigned to x1. In which case, your Shannon entropy will be exactly 0 because you don't have any uncertainty about the index of Z anymore. In the other scenario, if x1 is less than Z, then you will update your probability belief about the index of Z so that in each of the 99 remaining indexes, each of those indexes will have a 1/99 or 1.01% of being the correct index. And you compute the Shannon entropy in that posterior distribution too, which remember is the negative sum of P log P, which in this case is around 6.63. Now you will compute the average entropy because remember, we need to compute the average across different scenarios. Here we have 0 entropy again in this first scenario with probably 1%. Here in the second scenario is 6.63 with 99%. So we average across these two scenarios to compute the average entropy. And remember, this is the average entropy if you decide to perform the comparison between Z and x1. But you can go through the same procedure for x2, x3 to x100, right? So here's another example when you compare Z against x10. And there are three different scenarios. If x10 is greater than Z, then you will update your posterior distribution so that from x1 to x9, each of them has a 11% probability of being the correct index. The other scenario is x10 is exactly equal to Z, and the last scenario is when x10 is less than c. Each scenario has its own corresponding probability, as you can see here, 9%, 1%, 90%. In each of these scenarios, you once again compute the posterior entropy of the distribution, just like we did last time, and then finally compute the average entropy across the 3 different scenarios, weighted by the probability of each scenario. So this is the entropy when you do the comparison with x10. But once again, you can do this comparison across x1 to x100, right? And plot it as a function of the index that you want to inspect, the location that you want to inspect. And what you see when you compute this average posterior entropy quantity is that the average posterior entropy is at its lowest on average if you were to inspect the location right in the middle, because it allows you in either scenario to rule out half of the array to find the index that you're looking for. So we pick out the comparison that has the lowest expected entropy according to Bayesian experimental design. And in this case, this is exactly the location in the middle to do our comparison. And this, if you are familiar with the concept, is exactly binary search, which is a very classic search algorithm in computer science, which shows that binary search is actually a special case of Bayesian experimental design with a uniform prior on the different indices in the array. So this shows that this Bayesian experimental design framework is a very powerful framework that allows you to recover a lot of different search algorithms that you might be familiar with in computer science. Okay, so I'm running out of time, so let me quickly talk a little bit about how you can actually do Bayesian experimental design in Python. Oh, this is actually another example of how Bayesian experimental design is actually used in the real world. Let's imagine that you are a disease scientist and you are interested in studying the infection rate of a disease, and you build a model based on this infection rate where people randomly become infected according to some unknown rate that you want to model. And what you can do to perform experiments is you want to inspect how many people are infected at a specific time step, and from there estimate the unknown transmission rate. Here is how you actually do it using Bayesian experimental design, where at the top, it represents the evolving distribution that represents a belief about the transmission rate. And at the bottom, it's the different data points that you are picking to refine this distribution, this belief. And as you can see, the more data that we gather, the more refined this probability distribution becomes to be as close as possible to the true transmission rate that we don't know. So this is a very powerful framework that we can use to study transmission rates as well. And this gives you much better result than when you just perform random experiments. You're just picking random data to train your model. Bayesian experimental design can lead to much better lower error. Okay, I'm running out of time, so let me quickly wrap up this talk by telling you a bit about what different names this experimental design can have in different fields. Basically, it's you can think of it as a detective search for clues, where you just try to look for different ways to gather clues to either to refine your hypothesis, right? And this has different names across different fields. Can be called experimental design, Bayesian experimental design, or optical experimental design in statistics. In engineering, people usually call this a generalized form of design of experiments. In machine learning, we call it active learning or adaptive experiments. But there are so many other different names to point to the same idea. To finally wrap it up, there's this library in Python called opt-based experiment, which basically helps you implement Bayesian experimental design in Python, and the API is very easy to use. I'm not associated with this project, but I've been using this from time to time, and I think it's quite a useful tool. Finally, I know I'm way over, but just to wrap up, I recently wrote a book on Bayesian optimization. It's a special form of Bayesian experimental design. When you use it to optimize for an unknown quantity of interest, you want to maximize or minimize that quantity. I gave a PyData talk last year and the year before on this too, so feel free to search on YouTube for these talks. And you can use this discount code that I got from my publisher to get discounts on many books that they are running special promotion on. And if you're interested in this book, you can also email me to get a free ebook if you're one of the first 5 people to do it. Thanks again for your interest in this talk. And because I'm way out of time, please let me know what questions you have via email or other social media.
All right. Thanks, Quan. I'd like to invite you and everyone else to continue the conversation on Discord. And there's certainly people who would like to see if you got a notebook and a copy of your slides. Thank you so much, everyone.